Happy day! Tests like Fermat primality test and Miller-Rabin primality test can be used to check if a number is composite or prime. To find the factors of n, quadratic sieve and exponent factorization method can be used. Now we turn to the RSA challenge that was thrown open to public by authors. How this RSA can be used as an application to treaty verification and the advantage behind the public key concept. When the RSA algorithm was first made public in 1977, the authors made the following challenge. This is how the RSA module was described. N was chosen as a large number consisting of 129 digits as seen here. With the encryption exponent E as 9007, ciphertext C was obtained. Now the challenge was to find the message. The only known way of finding the plain text is to factor n. When RSA was made public, factorization methods that were available during that period would take a very long time, say 4 into 10 to the power of 16 years, to factorize the given n value. So, the authors came out with an idea of offering $100 to anyone who could decipher the message before April 1st, 1982. Only in 1994, 4 of them succeeded in factoring n. They used 524339 small primes, namely those less than 1633610, plus they allowed factorizations to include up to 2 large primes between 1633610 and 2 to the power of 30. The idea of allowing large primes is if one large prime q appears in two different relations, these can be multiplied to produce a relation with q squared. Multiplying by q to the power of minus 2 mod n yields a relation involving only small primes. Many of them were working on this problem, and after 7 months they obtained a matrix with 524339 columns and 569466 rows. A fortunate aspect about this matrix was the matrix was sparse matrix. It is a well-known fact that in a sparse matrix, most of the entries of the matrix are zeros. So, this helped in efficient storing, though it was a large matrix. Then, Gaussian elimination method was used to reduce the matrix to a non-sparse matrix with 188160 columns and 188614 rows. After few computations, they found 205 dependencies. The first 3 yielded the trivial factorization of n, but the fourth yielded the factors. Ultimately, the problem was solved and the values of p and q, namely the factors of n, were as shown here. Computing 9007 to the power of minus 1 mod p minus 1 into q minus 1 gave the decryption exponent d. Calculating cd mod n yielded the plain text message. The plain text was then converted to a message using a equal to 1, b equal to 2, blank equal to 0. Now we shall move on to see how RSA can be used for treaty verification. Generally, treaty is a formally concluded and ratified agreement between countries or states. Now, we move on to the example to demonstrate this aspect. Countries A and B have signed a nuclear test ban treaty. Each country wants to make sure that other doesn't test any bombs. Now, is country A going to use seismic data to monitor country B? Before proceeding, we must know what seismic is. It is the geological surveying method involving vibrations produced artificially by explosions. Country A wants to put sensors in B, which then sends data back to A. Two problems arise in this scenario. First, country A wants to be sure that country B doesn't modify the data. And the second one is country B wants to look at the message before it's sent to be sure that nothing else such as espionage data is being transmitted. Espionage is the practice of spying typically by the government to obtain political and military information. This is the reason why country B wants to look at the message before it's sent. These seemingly contradictory requirements can be met by reversing RSA. First, A chooses n equal to PQ to be the product of two large primes and chooses encryption and decryption exponents E and D. The number n and E are given to B, but P, Q and D are kept secret. The sensor collects the data X and uses D to encrypt X to Y congruent to XD mod N. Now, both X and Y are sent first to country B. Country B checks that YE is congruent to X mod N. If so, it knows that the encrypted message Y corresponds to the data X and forwards the pair XY to A. Country A checks that Y power E is congruent to X mod N. If so, A can be sure that the number X has not been modified. If X is chosen, then solving Y power E congruent to X mod N for Y is the same as decrypting the RSA message X, and this is believed to be hard to do. B could choose a number Y first, then let X congruent to Y power E mod N. But then X would probably not be a meaningful message. So A would realize that something had been changed. There are several implementations of public key cryptography, but very prominent one is RSA. A public key crypto system is built up of several components. First, there is the set M of possible messages, that is, the potential plain text and ciphertext. There is also the set K of keys. These are not exactly the encryption or the decryption keys in RSA. A key K is a triple E, D, N with ED congruent to 1 mod phi of N. For each key K, there is an encryption function EK and a decryption function DK. Usually, EK and DK are assumed to map M to M, though it would be possible to have variations that allow the plain text and ciphertext to come from different sets. These components must satisfy the following 4 requirements as seen here. Requirement 1 says that encryption and decryption cancel each other. Requirement 2 is needed, otherwise efficient encryption and decryption would not be possible. Requirement 3 is what makes the system public key. Because of 4, a user can choose a secret random key from capital K and obtain functions EK for encryption and DK for decryption. It is difficult to determine DK from EK. Hence, it is possible to publish EK without compromising on the security of the system. Let's now see how RSA satisfies the 4 requirements. All non-negative integers are considered for the message space. Key for RSA is a triple K equal to E, D, N. The encryption function is EK of M is equal to M power E mod N, where we break M into blocks if M greater than or equal to N. The decryption function is DK of M equal to M power D mod N. Again, M can be broken into blocks if needed. Functions EK and DK can be determined from K and are easy to compute, which shows that requirements 4 and 2 are satisfied. They are inverses of each other since ED is congruent to 1 mod N. So, requirement 1 is satisfied. If we know EK, it means that we know E and N. Then, it is computationally infeasible to determine D and hence DK. Therefore, requirement 3 is satisfied. Thus, public key system has been set up and checked for requirements. Once a public key system is set up, each user can generate a key K and determine EK and DK. The encryption function EK is made public while DK is kept secret. If there is a problem with imposters, a trusted authority can be used to distribute and verify keys. It is time to turn towards authentication and non-repudiation of symmetric key system and public key system. In symmetric key system, B can be sure that a message that decrypts successfully must have come from A or someone who has A's key. Only A has been given the key, so no one else could produce this ciphertext. Therefore, authentication is easy, but non-repudiation is not. Non-repudiation makes it very difficult to successfully deny who or where a message came from, as well as the authenticity and integrity of that message. But in a public key system, anyone can encrypt a message and send it to B. B will not have any idea where it came from. It is difficult to prove that it came from A. Hence, more steps are needed for authentication and non-repudiation. This can be achieved with the following 4 steps. When these 4 steps are followed, A cannot deny to have sent the message. It is possible to use one-way functions with certain properties to construct a public key crypto system. Let f of m be a invertible one-way function. This means f of x is easy to compute, but given y, it is computationally infeasible to find the unique value of x such that y equal to f of x. Now, suppose f of x has a trapdoor. This means that there is an easy way to solve y equal to f of x for x, but only with some extra information known only to the designer of the function. It is computationally infeasible for someone other than the designer of the function to determine this trapdoor information. If there is a very large family of one-way functions with trapdoors, they can be used to form a public key crypto system. Each user generates a function from the family in such a way that only that user knows the trapdoor. The user's function is then published as a public encryption algorithm. When A wants to send a message M to B, A looks at B's function fb of x and computes y equal to fb of m. A sends y to B. Since B knows the trapdoor for fb of x, B can solve for y equal to fb of m and thus find m.